Hey everybody, this is going to be a brief thermodynamics review before the upcoming quarterly. That is a fully multiple choice assessment. So many of the key concepts that we will be exploring today will most likely show up on the upcoming assessment. So we're going to look at how energy, heat, and work interact in thermodynamics using this PHET simulation. You can find this simulation on the phet.colorado.edu website. It's called Gases Intro. You can follow along with the video, or I suggest that you guys take a look at this simulation after the video to better understand how some of the things that we discuss in this video work on your own. So let's dive into it. First, we're looking at an isothermal process. So an isothermal process just means that the temperature remains the same. Remember that iso just means that something is staying the same. So we just added some gas particles to this container. We can see that they start to expand, and we are not adding any heat or cooling the system down. So the change in internal energy is zero. The energy transferred to the system by heating is zero, and Q equals W. The energy transferred to the system by heating equals the amount of work done, which are both just zero. So we can see that pressure remains the same, volume remains the same, because temperature remains the same. If we were to increase temperature, we can see that pressure increases. If we were to decrease temperature, we can see that pressure also decreases because volume is remaining the same. So this is going to look like your typical PV diagram, pressure versus volume diagram, which just looks like a hyperbolic curve for an isothermal process. Now, we saw what happens when we add heat or cool the system down. What happens if we change the volume? If we increase the volume, pressure decreases. If we decrease the volume, pressure increases. We can see this because temperature is directly proportional to pressure times volume. If temperature remains the same, but volume increases, pressure will decrease. If volume decreases, pressure will increase. So this should be fairly easy to understand, shown by the PHET simulation. Just know that temperature is directly proportional to pressure times volume. But we want to know why, when we increase the volume or decrease the volume, the pressure changes. So when we increase the volume, pressure decreases because pressure is defined by the force perpendicular divided by the area. You can find this under thermal physics on your formula sheet. So basically, pressure is inversely proportional to area. When the area of these container walls increases, pressure decreases, and vice versa. So ultimately, in an isothermal process, temperature stays the same, volume and pressure both stay the same. If we increase temperature without changing volume, pressure increases, and vice versa. If we cool it down, pressure decreases, volume stays the same. If we change the volume, pressure decreases if volume increases, and pressure increases if volume decreases. So that's it for an isothermal process and some things that you can do to the system when temperature remains the same or you change it. So now we're moving on to an isobaric process when we try to keep pressure constant while heating. So let's reset this system, add some more gas particles, let them expand, and remember that isobaric is just keeping pressure constant. So to keep pressure constant while we heat the system, we can see that pressure does not remain constant, and it increases when this system is being heated. So in order to keep pressure constant, we want to increase volume. As described before, when we increase volume, pressure decreases. So we basically want to cancel out the fact that the system is being heated by increasing volume to keep pressure the same. I hope this makes sense. It's basically just working with the formula T equals PV, because temperature is proportional to pressure times volume. It's basically just taking a look at what happens if temperature increases and volume stays the same. We're just playing around with those variables, taking a look at different situations. So, yeah. Let's move on to the isochoric process, which we already described with the isothermal process. It's basically just keeping the volume the same. Remember that isochoric is just another synonym for isovolumetric. So if we add gas particles to the system and we let them expand and we keep volume the same, we can see that pressure stays unchanged. But if we heat the system and volume stays the same, pressure increases and vice versa if we cool the system. To keep volume constant, if we were to keep volume constant and not change the internal energy by heating, we can see that work equals 0 and the change in internal energy equals 0. If we were to heat the system, the change in internal energy increases, which equals to the energy transferred to the system by heating. So again, no heat being added, the system's not being cooled down or heated. Delta U equals 0, Q equals W, which equals 0. If we did add heat to the system, we can see that delta U equals Q minus work, and the change in internal energy equals the energy transferred to a system by heating, which is just delta U equals Q. Now we're going to be talking about an adiabatic process. I can't really show how that works in this PHET simulation, so I'm going to try my best to describe it. It's basically when the system is insulated, so there is no heat exchange. Q equals 0, so delta U equals negative work. And I would show how the temperature drops when the gas expands adiabatically, but I can't really do that in this PHET simulation, and there is no other one where I really can do that. So again, I'm going to describe it. So basically, if a gas expands, it does work on the surroundings, loses internal energy, and temperature decreases. If a gas is compressed, work is done on it, internal energy increases, and temperature decreases. You can see that with a piston, when there's gas trapped in a piston, and you compress the piston or expand the piston. We did this in class with a syringe. So when you quickly pull the piston outward, the gas expands quickly, and the temperature drops. That is because the gas is doing work on the surroundings, but no heat enters, so its internal energy decreases and the gas cools. And this will happen oppositely for when you quickly compress the gas. Additionally, just remember about the laws in thermodynamics, such as the second law of thermodynamics, which just shows how heat flows spontaneously from hot to cold. No process is 100% efficient in the real world. Some energy is always lost as waste heat. And again, just take a look at these PHET simulations on your own to truly see how some of these things work in thermodynamics. So, thank you guys all for watching. Remember to subscribe to my YouTube. Turn on notifications. I will remind you guys to do that in some of the videos, since I can't really send these videos to everybody. So just enable notifications. You guys will see when the next videos come out. And I'm trying to reach maybe 150 subscribers before Thanksgiving. So please help me out. Help advertise my YouTube. So yeah, thank you guys so much. Good luck on the quarterly.